Hi students, in this lesson, we're going to understand something about the design of the CPU. As we discussed yesterday, it's all about the CPU design we need to start with because the computer system heart is the CPU itself. That is, when you talk about a CPU design, there will be several entities that are needed to be designed in the CPU. The CPU design will talk about initially the register design. That register design, in fact, is going to store, okay, by means of a register design, we're going to store the instructions that are being executed concurrently. All right. Yesterday I told you that should be a provision for the instructions that are getting executed concurrently within the CPU. A program is all about the collection of instructions which are available in the main memory. When CPU decides to execute the program, it has to execute the instructions one by one. Okay. So every instruction, when it is fetched by the CPU, it has to be made available in the CPU till it gets executed. For that, we need to provide a storage logic within the CPU for the instruction to be residing temporarily. That is, the instruction should be stored within the CPU as long as it gets executed. Okay, for that, we need to provide a register set. This register set can be organized in multiple ways. There are several ways to organize your register set. That could be either single accumulator or general register or stack organization. Try to understand that there are several registers in the CPU. What is a register first of all? A register is a collection of flip-flops. Let us try not getting into the details of the digital logic. A register is going to offer you a storage provision in terms of a few bits. That is, a register size can be 1 byte or 2 bytes or 3 bytes or 4 bytes. Depends on the computer architecture. We'll come to the topic in a short while. So eventually the register is going to provide you a storage provision for storing a word. The size can be 8 bits to 64 bits. We'll talk about that in a short while. There are several registers available within the CPU. All these registers must be organized in a proper way to get the efficient architecture, which serves as a best architecture for executing the programs. These registers can be organized in three ways. The registers which are available in the CPU can be organized in these three different ways. First one is single accumulator organization. Second one is general register organization. And the third one is a stack organization. Okay, so now we will start designing the register set. We need to adopt one of these organizations and then we start design the register set. But before we design the registers, let me tell you, we need to understand the basics of the main memory because both registers and main memory stores the data, right? What is main memory? In main memory, we're going to store the programs. And when it comes to the registers, these registers are going to store the instructions of the programs. So the huge logic behind this storage is the main memory. If we can understand the storage logic at the basic level, then we'll be able to design the register set. Let us go understand the memory logic. See, this is main memory, let us say. In this main memory, let us have a look at that. This is the main memory. This main memory, just try to understand, will be divided into two parts. One is the instruction part and one more is the data part. It is not written here. It is the instruction part and this is called data part. Okay, it's the instruction memory and the data memory. Okay, so What is the instruction part and data part? When you execute the instructions, all these instructions will have to be executed within the CPU. First, we need to understand what is a program behind this. A program is a set of instructions, I told you that all these programs must be residing within the main memory. Okay. So when you execute a program, that program should initially be loaded into the main memory. This program will have two parts. One is instruction part and one more is data part. Data is not visible here. It has to be written data. It's an instruction memory. It's a data memory. The program has two parts. When you write a program, that program will have two parts. The instructions that are available within the program and the data elements that are to support the program execution. That is, whenever you declare a variable, that variable is nothing but the data part of that particular instruction. Every instruction will have its respective data part. So when you try to execute a program, the instructions of the program will get stored in the instruction memory. The data items of the program will get stored in the data memory. Okay, so that is the difference between instruction memory and the data memory. The total main memory will be physically divided into these two parts, instruction memory and the data memory. Okay, here you can clearly see this is the instruction memory and this is the data memory. Okay, so now this main memory will be of some size. This main memory will be of some size. The main memory size will be measured in terms of words. There are several words. There can be several words. Okay. So here, if you want to locate a specific location, it will be located by its address. Every location will have its address. Okay. If you have 10 locations, all these addresses must be in between 0 to 9. The first address, second address, third address, fourth address, till ninth address. So if the size of the main memory is total 10 words, the address part will be 0 to 9. Okay, so we'll be able to locate any of the location by its specific address. Okay, so you can clearly see this total main memory will have two fields. One is address field and one more is word field. The address field is going to represent the address and the word field is going to represent the data which is available in this specific word. Okay, once again, the address field is going to represent a locations label. Okay, this is the 23rd address. And the data field is going to talk about the data item which is available within the specific address. Okay, so this is the address field and this is the data field. Okay, so this data field can be either instruction and the actual operand. Okay, so in the instruction memory, we are going to have the instructions. In the data memory, we're going to have the data operands. Okay, so the inside word field, either it can hold the data item or it can hold the instruction item. I hope you got it. So now, when you talk about memory, when you want to design the main memory, you need to keep a few things in your mind. That is, the question is, what is our architecture size? This can also be called as a CPU size. And what is our memory size? And what are the different addressing conventions? We try to understand what all are these about. Okay. Now, first one, when you talk about the architecture size or the CPU size, this architecture size can be of 16 bits or 32 bits or 64 bits. What is this architecture size? Let me tell you. Okay. Inside there is a word, right? This word will be of some stipulated size, a specific size. The size can be either, this word size can be either 8 bits or 16 bits or 32 bits or 64 bits. That could be 1 byte, 2 byte or 4 bytes or 8 bytes. Okay, so that is the size of the word, right? This size of the word is nothing but your architecture size. The computer system, when you try to buy a CPU, the CPU size will be measured in terms of some bits, right? When you buy i9 or i8 or i5 or i3, whichever processor you purchase, you will be provided with a measurement. What is that measurement? This processor is of 32 bits. This processor is of 64 bits. What is this in fact? There is nothing. In fact, this is nothing but a size of one word in the main memory. Okay. If it is a 64-bit architecture, if it is a 64-bit processor you're purchasing, that means that one word in the main memory is of 64 bits, is of 8 bytes. Okay. So that is what the architecture size all about. Okay. This can also be called as CPU size. So if the architecture size is 16 bits, then that means that every word size within the main memory should be equal to 16 bits. If it is 32 bits, every word in the main memory should be equal to 32 bits. If it is 64, every word in the main memory should be equal to 64 bits. The next thing that we need to understand is, before we design the main memory, what is the size of the main memory? Okay, so you know that the main memory size, I mean, most of you people purchase the memory chips, right? The memory chips can be 1 GB or 2 GB or 4 GB or 8 GB. Nowadays, it even goes to 16 GB or even more. But now, when we design the processor, we, as we're designing a basic processor, we will take the simplest memory. Okay, the memory size can be 1 GB to or 16 GB. Now, we are going to design our memory with 4K words, 4096 words. Okay, that means that the memory size is a total of 4096 words. This is the 0th word, and this is the 4095th word. This is the first word, and this is the last word. Okay. And when you define the size, you should also define the address field. How many bits that are required to represent every address. If it is 4096 words, the address field must be 12 bits. Try to understand. Because 4096 will be equal to 2 power 12, right? 4096 is equal to 4K words. 4K is equal to 2 power 12. 2 power 12 meaning, 2 raised to 12 meaning, here 12-bit address must be present. If you do not use 12-bit address, you can't address the locations properly. If you use 12 bits, 12 bits are sufficient enough to address any location here, to address any word here. So the address range must be in between 12 zeros to 12 ones. The first address of the main memory should be equal to, first address of the main memory should be 0000000, total 12 zeros, and the final address will be 12 ones here. Okay, so the address part of the main memory should be equal to 12 digit. Okay, and try to understand, as we discussed about the memory basics, as we're discussing about the memory basics, now this is the right time to design a simple main memory for the processor we are already designing. What is our job right now? We need to design a processor. In order to design the processor, we need to design the register set. In order to design the register set, we have to design the memory initially. If you don't design, at least we need to understand what is the capacity and size of the main memory that we do have. Our main memory is constructed with 4096 words, in which the address part is 12-bit. Okay. And in one word in the main memory, in our architecture that is being designed is 16 bits. Okay, that means that we are designing a simple computer system, simple CPU, in which we have taken an architecture size that is of 16 bits. And we have designed our memory with 4096 words. If it is a 16-bit architecture, every word in the main memory is equal to 16 bits. And as the main memory is equal to 4096 words, the address part must be equal to 12 digits. So by using 12 digit, any of the location in the main memory can be identified by 12-bit address. So anywhere in between 12 zeros to 12 ones, anywhere in between 12 zeros to 12 ones, you will be able to address a specific memory location. So the address part must be equal to 12 digit in our architecture, and the data part should be equal to 16 bits in our architecture. Okay, so another thing that we're going to understand when we design the memory is nothing but the addressing conventions. What do you mean by addressing convention? In what way you are going to address the memory? There are two addressing convention. Stay focused. One is word addressing, one more is byte addressing. Let us stay focused. Here, one word is equal to 16 bits, right? One word is equal to 16 bits. So this word part is 16 bits. I hope you got it. When it is 16 bits, of course, you need to understand this 16 bits will be constructed by using 2 bytes. Every word is designed with 2 bytes because 16 bit will be equal to 2 bytes. Okay. Now here, in order to address a specific location in the main memory, you can have two choices. One is you go by byte addressing. That is, every byte will be given an address. One word is of 2 bytes, right? So in which each and every byte will be given an address. So one word will get 2 addresses. And in word addressing convention, rather than bytes, we will give an address to every word. I hope you are following carefully. That is, when you try to give byte addressing, every byte will be given an address. So this is the first word. First word will have 2 addresses because every word is designed with 2 bytes. So 0th byte, first byte. So first byte, first word will be getting 2 addresses. Second word, of course, 2 addresses, 2, 3, 4, 5. Similarly, total every word in the main memory will be given an address. Every byte rather, bigger pardon, every byte of the main memory will be having its unique address. One word will be equal to 2 addresses because one word is equal to 2 bytes. Okay. When it is word addressing, our life will be very simple. We don't need to address every byte. Rather, we need to give an address to every word. Okay. That means every word, total number of words are equal to 4096. Okay. Forget about number of bytes within a word. Go to every word and give an address. This is 0th address, first address, second address, third address, fourth address. Okay. But when it is byte addressing, this word will get 2 addresses. 0, 1. This word will get 2 addresses. 2, 3. This word will get 2 addresses. 4, 5. This word will get 2 addresses. 6, 7. Okay. But in word addressing, every word will be given an address, which means that in byte addressing, every byte will be given an address. In word addressing, every word, regardless of the number of bytes inside, every byte will be given an address. Sorry, every word will be given an address. That is the difference between word addressing and byte addressing. Okay. Now, as we discuss the basics of the main memory, now we are all set to design our register set. Once again, just understand what we learned here in the memory. In the memory, first of all, you need to understand a computer system requires a main memory to store all the programs. For that, this memory should be divided into 2 physical parts. One is instruction part and one more is data part. In the instruction part, your instructions are going to be stored. In the data part, the data items of your instructions to be stored. Okay. And try to understand one thing. This instruction memory is contiguous and the data memory is non-contiguous. A simple thing is, simply if you want to understand contiguity and non-contiguity, let us say the instruction. What is the nature of instructions? The nature of instructions are one by one. When you want to execute a program, that program should be executed as a bunch. A program is a set of instructions. If you do have 100 instruction, first you will be able to execute the first instruction, followed by the second instruction, followed by the third instruction. So there is a specific order to execute your program, correct? So when you want to execute the instruction, when you want to execute a program, all these instructions must be residing in contiguous memory locations. Contiguous memory locations. First instruction should be here. Second instruction should follow the first instruction. Third instruction should follow the second instruction, and thereby each and every instruction are going to follow the preceding instructions. So the instruction memory is contiguous, should be contiguous, which provides a proper alignment of each and every instruction, one after another. Second thing is data memory. This data memory, in contrast to the instruction memory, is considered to be non-contiguous. This data memory is non-contiguous. What is non-contiguity? The elements for these instructions need not be in contiguous locations. That means that the elements of this instruction need not be arranged in a proper order. First instruction's memory operand can be available here. Second instruction memory operand can be available here. So you need to understand data memory is non-contiguous. So let us say we do have an instruction that is the 23rd instruction. 23rd instruction's memory operand is available in, let us say, this 256 data memory location. Okay, that doesn't mean that this 24th instruction's data operand will be available in 257. The 24th instruction data operand might be available somewhere later, maybe 386. 25th instruction's data operand might be available in second memory location. That is, these instructions are only contiguous, not the data words. Contiguous instructions will be available in the contiguous locations. All the instructions needed to be contiguous, continuous locations, let us say. When an instruction is going to get executed, it is going to call its data operand from the data memory, right? So this 23rd instruction will have a data operand, which is available in the data memory. It will be called. 24th instruction, when it is getting executed, it is going to call its data operand from the data memory. These instructions 23 and 24 need not have their data elements present in the successive locations. These operands can be scattered across the main memory. This is what the non-contiguity nature of the data memory. So the thing is, instruction memory is contiguous, data memory is non-contiguous. Okay, so then we got the basics in memory. Of course, the memory for executing the programs, we need to have a main memory. In main memory, instructions and the data elements of program will get placed. Instruction of your program will get placed in the instruction memory. The data operands of your program will get stored in the data memory. Instruction memory is contiguous. That is one after another. Data memory need not be contiguous. It is non-contiguous. The nature of the data memory is non-contiguous. The nature of the instruction memory is contiguous. So now we are all set to start designing our register set, having discussed these basics.